Section 2.3, Limit Laws. This is all from OpenStax Calculus Volume 1. And as we just talked about previously in the last section, we've discussed how to find limits from graphs and tables and sort of this intuitive way to look. We just kind of follow our graphs and take it where it leads us, or follow it where it leads us. Well, limits can actually be applied over sums, differences, products, quotients, and exponents, as well as radicals and several other we're going to call continuous operations. This is especially useful for polynomials and rational functions. So here are the limit laws themselves. If you have a limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is M, then if you sum the two functions and then take the limit, you get the sum of the limits. The difference of the functions, the limit gives you the difference of the limits. The product of the functions, that limit gives you the product of the limits, and so forth. These operations all work the way we'd like them to. Okay, so this actually works for radicals as well, and any exponent for that matter. So take those and remember those, and we're going to apply those in some pieces in a second. So we have another important theorem here. The limit of a polynomial, or more generally, a continuous function. If a function is continuous in an open interval around a, then the limit as x approaches a is f of a. We can evaluate it that way. That will come in very handy. Next, a rational function. If you have two functions that are both continuous, so the numerator and the denominator of our rational function here, if they're both continuous, then we can just evaluate at a, provided we are not dividing by 0. Dividing by 0 is not very good. We can't do that. All right, so let's take a few of these and evaluate. Well, we have a polynomial. We have 4x plus 2, so we can just plug in the value there. 4 times negative 3 plus 2, which is negative 10. Actually, let me give you some examples. Let's go back, because I want to make sure we are aware of what continuous functions are. So a few examples. Obviously, polynomials. Polynomials. Those are always continuous. Okay, those are all just powers of x. X cubed, x squared, etc. Exponential functions. Exponential functions are continuous. All right. Also, trig functions. Trigonometric functions. Specifically, sine and cosine. Be very careful with some of the others, but those are continuous along all real numbers. Okay. So those are some good examples. So all of these, and rational functions as well, as long as the denominator is not 0. So that actually applies to those as well. Okay, so the first one, it's a polynomial, it's a linear function. We can evaluate at negative 3. We can just do that because it's a continuous polynomial. All right, part B, this is continuous as long as we're not dividing by 0. So we are not dividing by 0 here. Our denominator is not equal to 0 as we plug in 2. So we can just evaluate this. This will be 2 times 2 squared minus 3 times 2 plus 1 over 2 cubed plus 4, which is 1/4. Is what that reduces down to. So again, because we're not dividing by 0, by that previous theorem, we can just evaluate. All right, part C, both of these are continuous functions. Okay, a radical function is also continuous. I did not list that, but that is one to know. We can plug in the value of 6. So 2 times 6 minus 1 times the square root, and we don't need parentheses there, square root of 6 plus 4. So that will be 11 square root of 10. And that's the value of the limit. We can just evaluate it as long as we're not dividing by 0 and they're continuous. All right. This is a very handy tool that is the first thing you want to try whenever you're evaluating a limit, is just plugging in if you can. All right, plugging in 3 will not make this 0. So we can just evaluate that. That is 2 times 3 squared minus 3 times 3 plus 1 over 3, switch that, 5 times 3 plus 4, right. That is 10 over 19. So the limit is 10/19. All right, and for this last one, the polynomial is continuous, so we can just evaluate at that right there, which will turn out to be -13. All right, evaluating is not that big of a deal. I mean, it's a great thing to have. It makes our lives a lot easier. However, the real question is, what do we do when we can't evaluate, when we can't just plug in? So here's the next example we've got. Evaluate each of these limits by factoring. Okay, if I plug in 3, or -3, that will make that to be 0. I cannot just plug it in. So we'll work with factoring. All right, so this is equal to the limit as x approaches -3. And that will factor, the numerator and the denominator actually factor. This will be x plus 3, x minus 3. That will factor as x plus 3, x plus 1. Now, because these two terms actually cancel out, that actually tells us that our graph has a hole at that point. That's why we can't evaluate at that point, but we are approaching a value at that point. Okay, so if we eliminate those two, limit as x approaches -3 of x plus 1 over x minus 3. Now at this point we can evaluate. It's going to be the same limit. It's a different function, but it is the same limit. All right, so that would be -2 over -6, so that would be 1/3. All right, let's work the same trick over here. Because if you evaluate at 1, it's actually a 0 divided by 0, so that really does not work. So that will be x plus 1, x minus 1 over x minus 1. That reduces down. Again, we have a hole in our graph. As x approaches 1 of x plus 1, which will be a limit of 2. Again, that tells we have a hole. All right, so factoring is one trick we can sort of pull. The next is multiplying by the conjugate. All right. So examine plugging in 5. That's always a good choice. Okay, try plugging in if you can. Well, the numerator would be square root of 4. 2 minus 2, that's 0 over 0. We cannot plug in 5. So we are going to multiply by the square root of x minus 1 plus 2 over the square root of x minus 1 plus 2. Okay, we are not changing the function itself. We are multiplying by 1. Okay, so we're getting this in a different form. So that would be x minus 1. The square roots would cancel. The outside and the inside terms cancel, so we get minus 4. Right, we get minus 4 there. And we have x minus 5, square root of x minus 1, plus 2. Now, if you notice, the numerator is actually x minus 5. So that reduces down. As x approaches 5 of 1 over the square root of x minus 1 plus 2. Plugging in the 5 now, that would be 1/4. Now I want to point out really quickly, this right here, we actually did not multiply by 0 because by plugging 5 in here, that's actually a value of 4 over 4, if you think about evaluating that. Okay, so that doesn't break any algebraic rules. We're just writing it, that expression, in a different form because there is some sort of hole or strange behavior happening there. Okay, part B, multiply by our conjugate again, so this will be square root of x plus 2 plus 1. Notice we're using the opposite sign there, the middle sign. So we have a minus 2, we'll use a plus 2. Minus 1, we'll use a plus 1. If it had been plus 1, we use a minus 1. X plus 2 plus 1. Okay. And I should have checked to begin with. If I plug -1 in there, we're dividing by 0. So I just automatically assumed we were making a mistake there, but that's what we need to do. So multiplying that, we'd get x plus 2 minus 1 over x plus 1 square root of x plus 2 plus 1. Okay, our numerator there is x plus 1. So that will cancel. That'll be the limit as x approaches -1 of 1 over square root of x plus 2 plus 1. And that limit, if we evaluate that at -1, will be 1/2. And there's our limit. All right, now let's have two more techniques that we've got to work with. If we have a complex fraction, okay, so both these next two are going to deal with fractions. If we have a complex fraction, now if you notice, if we evaluate that at -3, no dice. Okay, we cannot evaluate that because we're dividing by 0 at that point, but only in the denominator. Okay, that's something worth noting. So let's go ahead and write this. Rewrite that. Now I'm going to multiply through everything by x over 2 over x over 2. Okay, so I'm going to multiply this by, I'll go ahead and write all this, plus 1 over x plus 3. I'm going to multiply by x plus 2 over x plus 2. All right, that will give us the limit as x approaches -3. First denominator clears, 1 plus x plus 2 over x plus 3, x plus 2. Now notice I'm not factoring anything here because our numerator is x plus 3. So that means this is the same limit as x approaches -3 of 1 over x plus 2. And evaluating that, we get -1. All right. Next, if you evaluate 3 into each of these, you actually get a limit that fails. Okay, both of them are undefined at that point. So what we're going to do is combine the two fractions. All right, so the first one, let's see, well, this fraction is 4 over x minus 3 x plus 1. Yes, okay. So we'll multiply the first fraction through by x plus 1. So I'll have an x plus 1 over x plus 3, or x minus 3. X plus 1. Okay, minus 4, and we'll multiply that one. Well, actually, we'll leave that alone. X plus 1. Okay. Combining those two, we get an x minus 3 over x minus 3, x plus 1. Those will reduce, and that will be the limit as x approaches 3 of 1 over x plus 1. Evaluating that, we get 1/4. Right, so there are lots of tricks, algebraic really is what I come down to, algebraic tricks that we can use to evaluate some of these limits. Next, and the last, and it's the most important probably of these, is something called the squeeze or the sandwich theorem. So the basic idea is that if you have 3 functions, okay, and you know that we have a restriction here where one of the functions is stuck between the two. It's squeezed in or it's sandwiched between these other 2 functions. Then whatever the limits of the outside functions are, okay, so let me see if I can draw an example here. If we have a function like, say that is sine x, if we want to know the limit, okay, if we know that it's stuck between 2 functions at this point right here, if we know that it is, whatever those happen to be, then if we take the limit of the 2 outside functions, the limit has to go to the same place. That's the basic idea. Now this comes in very handy with sines and cosines because we know that sine and cosine are both between 1 and negative 1 always. No matter what their argument is, they are between 1 and negative 1. So let's go ahead and start out by saying we want to find the limit as x approaches 0 of x cosine x. Well, we know cosine's between 1 and negative 1. Okay, cosine is between negative 1 and 1. That means that x cosine x is between negative x and positive x. Well, if you take the limit as x approaches 0 of both of those, okay, so because of that, the limit as x approaches 0 of x, negative x, is less than or equal to the limit as x approaches 0 of x cosine x, which is less than or equal to the limit as x approaches 0 of x. Okay, so because of the scratch work we have over here, that must be true. Well, the limit over here is 0. The limit over here is 0. And so the limit x approaches 0 of x cosine x must be 0. So we can say the limit as x approaches 0 of x cosine x equals 0 by the squeeze theorem. It always begins with bounding something. Okay. So this next one, I'm going to go ahead and observe that x squared times sine of 1 over x is between x squared and negative x squared. We want to know the limit as x goes to 0. The outside function goes to 0. The inside, or the upper function, goes to 0. Therefore, the limit as x goes to 0 of x squared sine of 1 over x equals 0 by the squeeze theorem. Now, you might notice I've called it the squeeze and the sandwich theorem. Depending on what textbook you look at, you might see a different name for those. Okay, now number 8. I'm not sure of a good way to say that this is trapped by two things. We may need to appeal to some other algebraic techniques first. First thing I want to do is say that the limit as x approaches 0. Let's go ahead and use our conjugate to possibly not be dividing by 0. All right, so that would be 1 minus cosine theta over theta times 1 plus cosine theta over 1 plus cosine theta. All right, well, that would be 1. That's it. Its terms cancel, minus cosine squared theta over theta 1 plus cosine theta. Well, that is going to be sine squared theta. Now, I really hope that gets us where I want to go. Squared theta over theta 1 plus cosine theta. Now, provided these two limits exist, this will have the same value. Okay, so we'll see what happens there over 1 plus cosine theta. Okay, well, the first one goes to 1. We have shown that repeatedly in the last couple sections. So that's 1. If I evaluate that at 0, that is going to be 0 over 2. So this limit is 0. And this is actually a very important trigonometric identity. Now, this did not need the squeeze theorem, but it did appeal to several techniques here, one of which was our conjugate. Next was a trigonometric identity, and third was splitting this up into two fractions and evaluating. Okay, so This is probably a good one to end on and a good way to sum a lot of this up. All right, that's the end of section 2.3.